Our universe is an amalgamation of different objects following a wide spectrum of sizes, ranging from the smallest particles to the jumbo astronomical objects. Being able to perceive the nature and behavior of all these sizes has been one ultimate goal of mankind since ages. But as a single medicine cannot cure all the diseases, similarly, a single scientific theory cannot work well at all the scales. So, where we can efficiently describe the motion of a billiard ball or the motion of the planets around the sun, using the same laws we cannot describe the behavior of smallest entities in the nature. This is where quantum physics comes into picture. But what it really is, what led to the development of this theory, and how is it different from classical physics? This is Q&A, and here is the answer to the question, what is quantum physics? To understand what is quantum physics, we need to go more than 100 years back in time. We had pretty much figured out how the world works. We could explain the motion of objects around us, the waves on strings, the ripples in the pond, and even the motion of the planets around the sun. But when we think we know everything, nature throws us problems. There were three major events that gave birth to quantum mechanics. The first was in 1900 when a group of bulb manufacturers approached Max Planck. They wanted to make their bulbs more efficient. This required a better understanding of the famous black-body curve. Planck was confused on how to solve this problem. After a lot of brainstorming, he came up with an assumption. He said, energy in the form of light can only be emitted in discrete amounts. It cannot be emitted continuously. So, 1.4 units, 3.5 units, 6.2 units, etc. were not allowed. Planck did not realize the importance of this hypothesis. 5 years later, Albert Einstein, who back then was a struggling third-class patent clerk in Switzerland, realized the importance of Planck's work and used it to explain the photoelectric effect. This was the second blow to classical mechanics. The third and the final nail in the coffin of classical physics came from Niels Bohr. When we pass electric current through gas to ionize it and observe it through a spectrometer, we see very fine spectral lines. Their origin could not be explained by the existing theories. Bohr attributed these lines to the jumps made by electrons from one level to another. His theory was the first leap to explain the structure of the atom. So far, so good. But if this is what all quantum physics is, then why is it considered so weird and difficult to understand? Well, the answer to this lies in the physical interpretation of some of the offbeat concepts and principles involved in this. So now, let's have a look at some of the most interesting ones. Number 1. Quantum tunneling. Suppose you have a bouncy ball with you and you are hitting it at a wall. What happens? It keeps on coming back to you and you keep on hitting it. But there comes a point when it just disappears at the wall and then appears on the other side of it. Spooky, right? This is what quantum tunneling is. Technically speaking, a subatomic particle can pass through the potential barrier greater than its energy. Fun fact? This is the reason behind our existence. It is the basic principle involved in the production of nuclear energy in the core of the sun. Number 2. The wave-particle duality. In our daily lives or in the realm of classical physics, a particle is a particle and a wave is a wave. A particle cannot act like a wave, but in quantum physics it can. At the smallest scale, the wave nature of the particles becomes noteworthy. The last and the most interesting one is superposition. This means you can do exactly opposite things at the same time before someone looks upon you. That is, if you are a quantum particle, you can rotate clockwise and anti-clockwise at the same time before any measurement takes place. So, the Schrödinger's cat is both alive and dead until we open the box to check. You might be wondering, what am I even saying? But this is quantum physics and even the weirdest is normal here. And this is why Niels Bohr said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Share this video with your friends. See you in the next episode of Q&A.